We're moving on into the next page of our worksheet, and this introduces us to a new type of metal cation, a metal ion. It's called a multivalent. Now, iron is in the middle. Iron's the transition metal, and the transition metals don't really follow our octet rule the way that we've learned it. They still want to have a full valence shell. They still want to have a stable octet. We just can't really explain it with our simple models at this point of your career in chemistry the way that we have with the dots. So instead, what we do is we're actually going to tell you what charge it has, because these ones have multiple charges. They're called multivalent because they can have multiple charges. And if I have multiple charges, then the name can't just be iron oxide. Because if you look at the periodic table, you can find out that iron can either form a 2+ cation, or it can form a 3+. So if I just said iron oxide, you wouldn't know if I meant iron 2 or iron 3. Luckily, we've decided that we're going to make things simple for you, and we called this iron 3 oxide. Well, the 3 here directly relates to the 3 here. It's the charge on the iron. So I know that this is iron with a 3+ charge, so I don't have to worry anymore about guessing. I know.
Mr. Zapata, please go to the cafeteria. Mr. Zapata, to the cafeteria.
I know this is the iron with the 3+ charge. Now, oxide, the IDE, tells me this was oxygen. Oops. Oxygen. And oxygen, you either know is in group 16 and has 6 electrons, or you can just look right to it and know that, well, it's group 16, so it's always going to add those 2, so it's going to be a 2- charge. So an oxide ion always looks like that. Now here's the problem. 3+ and 2- are not neutral. 3+ and 2- still has one extra plus that I need to take care of. Compounds, like atoms, are always neutral. So if I have extra positive, I have to try and balance that out with more negative. But the only way that I can get negative in this compound is with another oxide ion. Another oxide ion. But now I have 3+ here and 4-, which means I don't have a 1+, I have one extra minus. Well, in order to try and balance that, I need to have more positive charge. Now I have 3 + 3 is 6+, and only 4-. So now I don't have neutral, I have 2 extra positives. And lucky for me, oxygens only come in 2s. By that I mean 2 charges. So this anion, this oxide, is 2-. Well, now I have 2, 4, 6 minuses, and 3 + 3 is 6 pluses. So this grouping of anions and cations is neutral. Therefore, that's going to be what goes in that box right here. And writing my formula, I just count them up. 1, 2 irons. 1, 2, 3 oxygens. My formula for iron 3 oxide is Fe2O3. And hopefully you notice that the 3 here is not the 3 here. That's not what that represents. The 3 here represents this plus charge. Now, if that was maybe a little bit outside of where you're comfortable with, there is a way that we can use our Lewis dot diagrams to figure this out in a not necessarily correct way, but a way that's enough for us. Iron 3 means it's iron valence of 3. You could sketch it out like this if you're more comfortable. And oxide is oxygen. It's group 16. 1, 2, 3, 4, 5, 6. And then go about it the same way we've done with all of the singular valent atoms. These two would go here. This one needs to go somewhere else. Well, the only place it can go is here. Oh, now I need more for oxygen. Now this is iron 3, so its valency is 3. Which doesn't really mean this, but it works if we're just figuring stuff out. Right there. And I still have 2 more spots. And I can end up with the same result. Those irons each lost 3. so they now are empty. And since I lost 3 electrons, I have 3 extra positives in my nucleus than I have electrons in my shell, so I still have 3 more positives, and these have 2 extra electrons than they had before. 1, 2, 3, 4. 1 there, and 1 there. So that means that it has 2 extra negatives in its shells than it has protons in its nucleus. I'm just going to use dots on this one. 2 minus, and 2 minus, so that's what would go, oh look at that, that's what would go there. And if I count them, 1, 2, 2 irons, 1, 2, 3 oxides, there they are. I get to the same point, so if you're still comfortable doing these as your rough work, then go right ahead, that's fine. Just read this number in the brackets as the number of electrons in the valence shell. I was looking through it and realized that once again we have oxide, so I was a little oxygen centric when I did this. So I just switched this to PbS2 so we could kind of look at something different than oxygen. Now, in this case, when we're given the formula, it gives us a lot of information, just like we saw in our previous example. This one tells me that it's lead and sulfur, which is awesome. So I can go right over here to the name. I know it's going to be lead and sulfur. And I know that we're going to change the ending to IDE. IDE. And so lead sulfide should be our name. Let's go ahead and come back to that. So this also tells me that there's one lead, and 2 sulfurs. 2 sulfurs. Now if I look at my periodic table and I look for lead, lead's in the middle. Lead's in group 14, it's number 82, it's Pb, but I realize that lead has 2 plus as a charge or 4 plus as a charge, and so now I don't know which lead it is. I don't know which lead from the numbers, and I don't know which lead it is because here the name I came up with was lead sulfide, but I don't know if it's lead 2 or lead 4, so I'm going to have to go a different way to figure that out. The way you figure it out is by working with the anions. So sulfur, I know there's 2 because the formula tells me there's 2. Well, sulfur is group 16, just like oxygen, so it has 6. It's going to gain 2 and become 2 minus. And if you're not sure about that yet, it's on your periodic table. It does tell you it's 2 minus, or we just keep working with our electrons and we'll just remember that. This sulfur is going to do the exact same thing because it's the same atom, so it reacts the same way. It's going to gain 1, 2, so if it gains 2 negative, it's there. That gives me a total charge of 4 minus coming from those, and this whole compound has to be neutral. And if it has to be neutral, it's going to have the same pluses and minuses. Well, the only thing that one lead has to be 4 plus to balance the 4 minus. So this is the lead 4 sulfide. This is the lead 4 sulfide. So I have to read the formula in order to figure out which one of those charges. Now, there is another possibility for lead. It could have been lead 2 plus. Well, how do I know? Let's say I get tripped up somewhere. How would I know? Let's say I guessed incorrectly and said, well, it's got to be 2 plus. Well, 2 plus and 2 minus neutralize, which means I don't need this other sulfur there in order to make that a neutral compound, so I would get rid of it. And if it was 2 plus, my formula would not be PbS2, my formula would be 1 Pb and 1 S. It would be PbS, and that would be lead 2. That would be lead with a 2 plus charge, sulfide. And so lead and sulfur actually can form 2 different compounds. It can form lead 4 sulfide, which is what we had originally, or lead 2 sulfide, which we have here. But just to make sure that we're all on the same page, lead 4 sulfide has 1 lead that's 4 plus. It has 2 sulfurs that are 2 minus each. I'm just going to sketch them out real quick. Typically we don't draw all these once we've got to this point, but I'm going to sketch them in. 2 minus, I should throw brackets for consistency. So lead 4 sulfide has 2 sulfurs and a 4 plus charge. Lead 2 sulfide has a 2 plus charge and only 1 sulfur. So different formulas, different names because they're different things.